This video tutorial will cover the faux analog PDK version 0.1, the installation, orientation, and training for that kit. This kit and this video was prepared by Sherlock MBV Consulting for Stone Soup Labs Incorporated. The content of this video involves installation of the kit, orientation of the kit and its use, in particular the files within the PDK and what the installation does to your home directory. Once we get an overview of that, the video will cover how to start Electric and to see how those two things, both the PDK and the files in your home directory, modify its behavior. Then we'll look at opening and managing libraries. We'll see how Electric manages libraries and some best practices that can be used to easily maintain libraries as projects. We'll also look at the different kinds of libraries, library formats that Electric supports. Once we get that overview, we'll drill into a CMOS example. We'll look at both the layout and the schematic and some of the details of navigating through those types of design files. And once we do that, we'll cover layout versus schematic comparison to make sure that we can have equivalent layouts and schematics. Then we'll look at some DRC examples, both real-time and hierarchical. Then we'll go into simulation. We'll simulate from a schematic and we'll look at the results in Electric's native waveform charting tool. And then we'll look at the same signals using PyLab as a more detailed way and a more flexible way to do analysis of the results. Then we'll do parasitic simulation out of the layout, and then we'll follow up with some drafting tips and tricks for icons, schematics, and layouts. So first we'll look at the installation procedure for the faux analog PDK. This installation has some basic assumptions. Number one, that the user is familiar with Linux shell commands and understands what the bashrc file does. And the other major assumption is that ngSpice version 25 is already installed. And in the case of Stone Soup Labs development environment, that's a known quantity. So we'll start by unpacking the PDK. We'll run the setup script, and then we'll finish the installation by modifying the bashrc, cracking open a new shell terminal, and then we'll move on to starting Electric. The environment that we're using today it's Ubuntu, so this is Ubuntu 12, which I highly recommend that be used for any design work. It's a very stable platform. There's a lot of good development going on. It's well supported, well funded, and it has a lot of good packaging for different utilities and different products. So in the home directory here, I've got the PDK, so we're going to unpack that. Inside the PDK directory, under the faux analog directory, there's a bin. So we're going to go into the bin library, and there's a script that will set up the kit. So what this kit installation script has done is that it's unpacked some reference libraries, some libraries that we'll use as examples, and that we'll be able to modify and edit. It's checked that if these path variables are set properly, that all the different executables that are used to run the kit are available. So what we need to do now is modify the bashrc file. So here in the home directory, what we're going to do is edit that file. And at the very end, we're going to change the path, and the script tells you what those path variables are. As you can see, I've already got them set, but I will copy them in for example's sake. So the path variable needs to be able to find the kit's bin directory, and also the Python path needs to be able to find the Python files inside the kit directory as well. So I'm going to start a new shell, and inside that new shell I should be able to find electric with the Linux which command, and it should resolve to the kit, and it does. Make sure we've got ngSpice. Let's make sure we've got our charting tools, our corner simulation tool. So those are the 4 primary executables that we need, and they are all on the path. So now we'll get some orientation inside the PDK and look at the files that were expanded in the PDK library. So I'm going to change directory into the PDK. And there are several directories in here. First off is the bin directory. It has 5 executables in it. It's got some of them are links to other executables elsewhere in the kit folder, but primarily they're either Java or Python scripts. The DE-lib contains 2 libraries. They contain the analysis library, which provides widgets for running simulations and setting different process variables. And then there's the prim-lib, which has the analog components that you need to design analog circuits. It has transistors, has a PMOS, NMOS, vertical PNP, and some resistors and capacitors. The .java file is a folder actually that is expanded and morphed into your home directory, and it contains a lot of different subdirectories that all support the different preferences inside Electric. Electric is actually a collection of a lot of different subprograms, and so many of those programs need preferences. So if we just look inside this, there's going to be a .preferences folder, user prefs, and under that it's the hierarchy continues into the Electric partitions. But many of these preferences are very specific to the kit, and so they're provided here. They're unfolded into your home directory, so that there's many of them, and many of them are buried within different preference settings. And so to make that simple, they're just unfolded into the directory for you, so you don't have to waste time figuring out where they are. The Java directory contains Electric itself. It contains the Electric binaries, the actual executable in the Java runtime environment. So inside here there are a whole collection of jar files that work together to make Electric work. There are plugins. There's 3-dimensional rendering tools in here, and all kinds of different support libraries that make Electric do the many things it can do. Also in there is a source directory. There were some bugs, so if you go through this README file and look at some of the descriptions in there, the source code that was modified to fix some of the bugs and to simplify the environment are all detailed in this README, and this is source code that is provided to Stone Soup Labs under the GPL license. So it's all GPL. It satisfies GPL. There's also a Python directory with some Python scripts, and there's a flow for developing these Python scripts, and there are some tools that are very handy for modifying them and making them more sophisticated. So you can consider these as starting points to do some charting for both DC, AC, and transient analysis. But they're just a starting point. You can do many other things with them, but there's enough in there to get some interested people and who want to do more sophisticated charting can grow those files or create new ones, more sophisticated ones if necessary. Most importantly is the SPICE directory, and inside it there are two SPICE files. There's the components.spy file and the process.lib, and those two files work together to allow us to run corners. Corners allow you to see different strengths of transistors and combinations. It's more appropriate for digital. If you want to do statistical design, again, that's all possible. It'd just be simply modifying the Python scripts that actually launch the simulations. So all the examples are in there, and they can be expanded upon. There's also in here an ODS file. The parameter calculator ODS file is a LibreOffice spreadsheet file that has some calculators in it for assisting in calculating resistances and capacitances based on geometry. So all the resistances are entered into electric as geometry parameters, not as actual resistance values. So that calculator is important for calculating resistances and capacitances. Finally, there's the training library, and that has the outline of the training video in it. So we've covered the executables, the DE-lib, the tool settings file, some of the examples that are available, and then the source code README, Python, and SPICE. So we'll move on to what the PDK files do to your home directory. And what they do is they put this .java directory into your home directory, which sets all the preferences for electric. It creates a libdirs file and link, so that which tells electric where to find different libraries, and then it unfolds the PDK into your home directory, a project with examples in it, and then also it creates a sim directory. So we'll go take a look at that next. So here in the home directory, we can see a libdirs file, and it is a link to the libdirs examples. So you can think of examples as a project. So if you have project A, project B, project C, you can anytime you can link to that project file and be looking at a different project. We only have one project in our home directory at this time, so the libdirs links to just this one file. So what we'll do is we'll also take a look in the project folder. There's the examples library that was placed there so that users can edit it. And inside it, it also has a libdirs file as well. So if I look at the contents of the libdirs file here, it's pointing into the project examples, which is pointing into this file here. If I more this one, I can see that it's actually pointing into the PDK. So the point of that libdirs file is it's recursive. So electric traverses the libdirs in that order and just accumulates the folders. So as far as electric is concerned, the libdirs file essentially flattens its world. So it sees all of those, all the folders that are in the libdirs file chain they appear to be all in one folder. So you can use this to to hard code dependencies between kits and libraries and projects. Finally, there's the sim directory, and there's nothing in it this time, but we're going to run some simulations, and right now the kit is assigning that library as the folder to collect all the simulation files, all the charts, all the simulation outputs go into that folder. Next, we're going to start the electric VLS design system and see a few of the ways that the PDK and the files in the home directory affect its behavior. So all we do to do that is go to the home directory and start electric. What we're going to look at next is the technology menus, and the electric kit has been greatly reduced in the sense that electric provides about over a dozen different technology libraries. So if you download electric from the electric website and start it in its native mode, you'll see over a dozen different technologies, printed circuit board technologies, TFT, deep submicron, BiCMOS, a whole variety of different technologies. But what we've done here is reduced the technology menu to a very simple list, and there are essentially 4 technologies that you use for working with this analog design kit. There's the artwork technology, which is predominantly used for creating icons or symbols. There's the MOS technology, which is used for drafting layouts. There's a schematic technology, which is used for drafting schematics. And then there's a generic library, which is essentially it's a hidden library, but there are elements of it that are available in both layout and schematics that allow you to glue things together. And we'll see an example of that when we get to parasitic extraction. So the technology menu library you can see here on the left. This is the MOS technology, and it's organized to enable easy drafting of layouts. But you can see here that this is a 5-metal process. There are different metals for interconnect, different metal pins, and then there are metal-to-metal via macros, which allow you to connect, for example, metal 1 to metal 2. There are different devices in here. There's a PMOS device, and it's got its P-active contacts, and then its N-well contact, and then correspondingly there's an NMOS transistor with its N-active contact and its P-well contact. Also, there's some resistors. There's some resistors that are diffusion types. There are some polysilicon resistors. This particular process has a poly 2 resistor, and then there's also a poly 1 to N-well capacitor as well. So it's got quite a few different components that we can use, and we'll go through some examples of that. Also up here on the right is a pad that allows you to connect the chip to the outside world. The artwork technology is used for creating icons and symbols so that you can leverage the hierarchy of the system to manage complexity. And the artwork is used for creating different glyphs and adding text to your icons so that they're useful and readable. The Library Explorer is also in the same tab, and then the different layers for the technology are also available. And the layers tab is really most useful when you're looking at the layout technology. You can see the different layers of the process turn them on and turn them off to see the interactions of the layers in the drafting on the drafting canvas here in the center. At the bottom, there is a dialog, which is where you'll see any error messages or any messages that will instruct you further, such as when you're running DRC or LVS, you'll get specific errors that you can then toggle through those errors and look at the effects in the layouts and in the schematics. Now that we've got electric open and we've been orientated in the tool, what we're going to do is open and manage some libraries. To do that, we go to the Explorer, and once we have this Explorer open, we can go and open a library. Now, what's happened is that the libdrs files that are all linked together are presenting us all the libraries they can find along those paths. And a best practice that I use is I create one library that contains load icons, and I give it a name with 3 capital A's at the beginning so that it percolates to the top of every alphabetized list. But if I open this library, it's going to ask me a few things, and generally when you see this file, just say use the above settings. But it loads all the libraries I need at once. And the libraries that are loaded in the order that's found in this particular schematic. So these are icons, and you can find these icons in every library. So by putting this icon in a single schematic, it's essentially a library list. The way that Electric works is that it uses a lazy library loading process, so it's always loading a minimal amount of libraries. So if you open up a top-level library and that library is referring to a dozen other libraries in dependency, it will go and search those libraries and load them as it finds them. And that's the minimalistic way to load data into Electric. In general, though, when you're getting started, that can leave a lot of interesting libraries unloaded. So what's recommended is to use this method where you create a library that just simply loads icons, one icon from every library that you intend to use during that project, so that you're always loading them. And this becomes more important when you're collaborating with a design team and those libraries might be in, for example, a CVS repository. So you might not be editing a library, but the CVS color codings in Electric will tell you when someone else is. So those are important things to keep in mind. So this is just one way to manage large projects with large design teams. But by default, Electric does use a lazy library loading method. Electric supports a couple of different library types. One is the JElib and the other is the DElib. And essentially the only real difference between these two formats is that the JElib puts an entire library into one file, and the DElib puts an entire library into a folder, and each cell gets its own file. And the DElib method is preferable if you're going to be using, for example, a CVS repository or some other repository for managing the files in the design, and there are multiple people working on the same library. So creating and managing libraries it's recommended to use DElib. One of the issues with DElib is that you need to keep in mind is that there is a dialog bug in when you do save as DElib. It sometimes you'll get a string DElib after JElib. So if you have a library named Bubba, it might be named bubba.jelib.delib. So just be careful in that form. It doesn't automatically populate the way you might think. Next, we'll look at a simple CMOS example. And to do that, we'll go through the different libraries that are used to simulate it and to analyze it. So there's the kit comes with an analysis library, which is a set of spice widgets for managing the process and the simulations, AC/DC transient. And then there's a primlib, which contains all the components of the process for schematics. And then there's a primlib test library, which has some examples in it, and we'll run some simulations out of that. And then we'll specifically look at a test CMOS example, which has a schematic and a layout. So the analysis library is shown here, and it has widgets for setting the temperature for the simulation, running through different process corners. TT is nominal, F is fast, PMOS fast, NMOS, SS is slow, PMOS slow, NMOS, FS is fast, PMOS slow, NMOS, and SF is slow PMOS and fast NMOS. So those you can sweep the different corners. And the next step, I think, in the development of this kit, probably version 0.2, is to add process variation, and then probably the step after that would be to add mismatch. But this just gives you an idea of the things that you can do to control simulation through very simple widgets. There's a small signal analysis widget. There's a one-dimensional transfer function widget. So if you want to sweep one voltage or one current source, you can do that and see the how that affects the operating point. There's also a two-dimensional one, so you can sweep two sources at a time and get a family of curves. And then, of course, there's the transient analysis widget, which allows you to set up a transient, the stop time and the time step factor. The most important library delivered here is the primlib, and it has a series of components. It's got resistors of different kinds. It's got a diffusion resistors, polysilicon resistors. It's got an NMOS transistor. It's also got a PMOS transistor. It has a PNP transistor that is fixed geometry. If any of these cells ends in fixed geometry, that means that you can't change the geometry. It's hard coded in the geometry. So whereas the other ones can be stretched in W and L, the fixed geometry cells are locked. And so if you need more of them, you literally drop down multiple instances of the same geometry, whereas the other devices can be stretched and pulled. There's a datasheets library, and this is a very early release of this library, but the idea is to provide an executable datasheet for every component in primlib so that the designer can see how that particular device reacts to process voltage and temperature variations. So, but this is a very early release, but I expect that the datasheet library will grow in time. So coming to it is this primlib tests, and so in here we've got several different examples. The one we'll focus on in this video is the test CMOS, and this is a block that has an icon view. So it's a very simple block with an input and output, power and ground, but it also has a schematic. There's also a layout view. So the layout view is the drafted representation of the schematic. You can run LVS from either the schematic or the layout. It doesn't matter. It will equivalence the two by name. So any two, if a schematic and a layout have the same name and they're organized in the cell in this way by name, whenever you run LVS, it will compare those two together. There are ways to compare a schematic of one name to another, but in general that's not recommended. it's better to keep the nomenclature and your naming of the cells equivalent. That way all the LVS is done very easily. Just a point of order here is looking at these devices. If I zoom in, we can see we've got some PMOSs here, and this ratio shows a width of 12 over a length of 2, and that device has one finger, so there's only one 12 by 2 device there, whereas this next one is got a width of 3 and a length of 2, and there are 4 fingers. So in total they're essentially equivalent. So when I run LVS, LVS is going to compare these numbers to the layout, and sure enough I can see that this is if I do Control I on this, I can see that that's got a width of a 12 by 2, and this device is a 3 by 2. Now LVS is no respecter of fingers, so it will do the calculations accordingly. As long as all the areas and lengths and ratios are equivalent, it's going to be satisfied. So for example, if I go in here and I change my transistor and I make this one a 1 by 12 as well, geometrically they're equivalent. Well, not geometrically, but mathematically they're equivalent. So if I run LVS, I don't get any errors. If I come back and I make this back a 3 by 2, I will get an error now in LVS because they don't line up. And it's telling me that the sizes don't match between the schematic and the layout. So if I go back and make this 4 fingers of 3 by 2, it's now right, and if I hit LVS, everything comes out clean. It's also good at this time to point out that whenever something changes inside an electric library, you can see that the text changes and it becomes bold. So that tells me that I've made a modification to this library. If I go in here and I save the library, everything goes back to normal case, and that means it's been saved to disk. So next we'll go into LVS, and we've covered a little bit of that already, but specifically we'll look at electrical checks, network tracing, and substrate checking, because those are all very important for these planar processes. So next we'll look at the layout view. Now Electric is heavily object orientated, so everything is an object. There's very little recognition of shapes and sizes. Everything is done by an object. So for example, if I come down here and I click on the VSS pin, it's going to highlight all the connections, and you can see that some of the connections flow through metal. Some of the connections actually flow through the well. And so if I zoom in here and we take a look at that connection, I can see that there's a well connection here as well. So on this end device, there's a P-well pin that's tying metal all the way to P-well. And so just by highlighting a signal, you can get a very clear view of how things are connected in the different runs. And this is really a valuable aspect of Electric, where you can see the networks and how they work their way through the layouts to each device. And a key thing to keep in mind is that when you see dash lines, that means it's an arc. If you see a solid line, that means that it's showing you the pin. So for example, if I zoom in really close on this PMOS up here, and I hover my mouse over the device, you'll see a little plus sign. That means that's a pin on a device. You can see one there. You can see one there. Now, if I want to connect to the well, how do I do that? Well, there's a special select for that. So This special mouse with, you can see that the mouse has this little glowing halo around it. When I do that, that allows, you see the little plus sign right over the center of that transistor. That allows me to connect to the back gate. So you can see there's a flight line from the back gate to the well contact. So when you want to connect to the back gate of a transistor, you need to switch to the special select, and that you turn that on and turn that off, because most of the time you're connecting to the source, the drain, or one end of the gate or the other. So, but when you want to tie into that to the back gate, you go to special select. It's important to point out at this point that that well checks are part of the LVS process. So as you can see, as I float my mouse over this connection, that is a NWell arc. So anytime you select a device, you'll see its description listed here in the lower left-hand corner of the screen. So if I select a transistor, I can see the transistor. But if I select this NWell, for example, right now if I run LVS, LVS is clean. But if this device is not properly connected to the body or the back gate of the transistor and I run LVS, I'm going to get an error, because as you can see in the schematic explicitly calls out the back gate connection. So it's going to rigorously check all the connections of the device. And so these are things that are very easy to miss, especially if you haven't been doing much layout in a while or ever. That it's easy to miss that connection. So for me to go fix this, what I do is I go to my special select mode, I select that, and I just wire them together. It's important to note that with electric routing arcs or wires, it's left mouse button to start and right mouse button to finish. Many other drafting tools, it's always left mouse button to start and finish, but with electric, you start your arc with left mouse button and you finish with right mouse button. So now if I go do my LVS again, everything's clean, everything's right. Control 9 is a zoom to fit, so that's a pretty handy thing to have in your muscle memory, is Control 9, which gives you a fit of both the schematic and the layout. So I'm going to go save my library, and now I have an LVS clean cell. One of the good things about electric is that it has a set of network connection checks. So if I just select any port, it will highlight everything else that it's connected to. If any port on any device, if I select that port, you'll see the port name there. For example, the gate is being highlighted. If I select that, I'll see all the other ports that it's connected to. Also under tools, there's some network checks that are pretty handy. So ones that are used quite often are just show the power and ground pins. Also under network is show all networks. So that assigns a unique color to each network in the schematic. And so those are just some handy things to keep in mind when you're analyzing a schematic or you're getting strange results. A lot of times it's because something is either shorted or floating, and those checks show very clearly that things are connected properly. If they're not connected, you won't see these little colored boxes floating around the ports. Those little box halos will not light up. So it's a great visual inspection tool for looking at schematics and how things are connected. So next we'll look at design rule checks and the layout, and there's a lot to study about that and go learn, but we'll do a few things. We'll look at the real-time DRC, the hierarchical DRC, and then we'll look at some antenna checks. So we'll open up the CMOS layout, and running hierarchical DRC is very simple. You just hit the DRC button, and what that's going to do is it's going to check all the geometry design rules for everything in this cell and anything beneath it. So all the subcomponents are checked, all the individual pieces are checked, and then everything that's connected together is checked as well. Electric does support dynamic DRC and real-time DRC, which is very, very handy. So if I were running metal by this cell and I wanted to move this wire in, I'm going to see the spacing rules superposed dynamically. And as soon as I get an error, I can back off a little bit and satisfy that rule. So that's a really handy thing, and it's most of the rules that are dynamic are the simpler rules, so spacing rules, notch rules, width rules. Those are the kinds of rules that are dynamic. Some of the more subtle rules you won't catch until you run DRC hierarchically. So that's an important thing to keep in mind. But for the most part, because much of what's happening in electric is object oriented, it's correct by construction. So you'll find that you'll have very few hierarchical DRC errors because of the interactive DRC that's going on all the time. Finally, we'll look at antenna rules. And so antenna rules basically make sure that the ratio of poly over active area is not swamped by the total poly area of any one polysilicon net. So if I run my antenna rules, I can go under my tools, I can look at electrical rule checks and look at the antenna check. I can see that I'm not getting any antenna rules. But if I were to take this polysilicon layer here and extend it, and then maybe make another piece this way, and then make it very wide, I could see if I can induce an antenna check. Not yet, so I'm going to zoom out and make this a very, very large piece of polysilicon. See if I can induce an antenna rule check here. And antenna rules are not working at the moment. We will get that fixed in version 0.2. Moving right along. So next what we're going to do is look at simulation from the schematic, and we'll look at the native charting tool inside Electric, and then also how to do some charting with PyLab. We'll be running ngSpice from a schematic simulation test bench, and then there's a native waveform inside Electric, and you get that through the wave button. And then we'll go outside of Electric to use PyLab, and we'll look at a way to manage signal lists. And this is really the recommended method for doing detailed analysis for post-processing waveforms from Spice and for working with very large designs. So as the signals list gets very large, Electric's the native waveform viewer starts to become less useful. So the general rule of thumb is if you're setting up a simulation and you want to look at just a few signals, the Electric waveform viewer is a great way to sort of do a lights on test, make sure everything's working okay. And then when you want to get into detailed charting and mathematics and post-processing analysis, it's highly recommended to use something like PyLab, where there's a lot of libraries for managing large vectors of data. So we're going to go to Electric, and we're going to look at the schematic first. So this schematic is calling these different devices, and we have a harness for this schematic called test CMOS harness. So I'll open up the schematic for that. And the block is located in a test bench, and I've got voltage sources, and I've got a capacitive load for this inverter. If I zoom in, I can see some Spice widgets from the analysis library I'm setting the temperature to 27 degrees. I've got process corners. There are 5 corners that you can use. I'm using only 3 of them in this analysis. And I'm going to be running a transient simulation. And the simulation is going to run for a microsecond with an initial time step of 1 nanosecond and a maximum time step of 10 nanoseconds. And from there, all I need to do to run this simulation is to hit the sim button. So it's running ngSpice and looping through the different corners. And then if I want to look at the results, I just hit the WAV file. And I'm going to navigate into the simulation directory. And every simulation, there's a unique folder for each simulation. So test CMOS harness has its own directory. And I can look at any of the raw files that I want to. So I've got the different corner raw files. So I'll look at the nominal raw file and open that up. And I'm going to associate that raw file with this schematic. And I can zoom in on the signals. Take a look at how they look close up. There are different things you can do in the electric waveform viewer. You can set some grid axis, and there's some measurement tools that you can do in here as well. You can use the measurement tool to look at voltage and time differences. It's got some handy tools in there they're very good. So by default, I highly recommend that you use the electric waveform viewer for doing functional analysis of your design. It's a great way to very quickly validate that everything's working and all your inputs and outputs are working the way you'd expect. It's got a great signal highlighting capability, so I can look at that my input is doing what I expect it to do, and my output is in the right place. My supplies are at the right voltage, and so it's a handy way to do a quick look at your results. Next, we're going to leave the electric waveform viewer and navigate to the simulation directory and use a different approach for graphing the results. So I'm going to go to the sim directory, and there's my test results. And I've got 3 raw files. If I want to look at all 3 waveforms at the same time, that's generally difficult for a lot of the native waveform viewer, because when you change the process variables, the simulator is going to be taking different time steps in order to calculate and converge on a result. So the time vectors for each simulation are very different. The time points that are saved are very different. So to be able to look at them all together in one waveform viewer, you need a modern waveform generation tool. So what we've got is, it's a Python script, and you can continue to evolve it, but it's called charts, and it comes with the kit. And so if you want to look at all of the waveforms together, the important thing to do is to look for these 2 files. First, there's a signal list, which gets written every time a new netlist is created. And there's also a chart list, which gets written, and as long as it exists, it will not be overwritten by the netlister. So what I'm going to do is I'm going to open up the chart list file in a text editor. And what it has is, it's got a list of all the signals in the design all the way through the hierarchy. So as your designs get bigger, this file gets bigger, and the signal depth gets deeper and deeper. So you'll have a top-level schematic calling lower-level subcircuits, so on and so on. And so the depth of the signal list can get very, 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 very long. And so being able to come back to this file over and over again, looking at the same signals repeatedly, this becomes very useful in the verification phase and the debug phase of your design. So the way this file works is pretty simple. Everything beneath the keyword uncharted is completely ignored. So it's anything above this line that comes into play. So this first command just basically sets the fonts that are used in the chart. So if you've got a very simple chart, maybe big fonts make sense. If you've got a very busy chart, you might want smaller fonts. But we're going to be looking at the corners that were analyzed. And so the first thing I'm going to do is I'm going to take my output and I'm going to copy it and put it up into this list. So I have my output, and maybe I want to compare that with my input. And then I want to look at overshoot and undershoot. So let's put the ground and the supply in there as well. So if I want to put that into a stripe, all I got to do is copy a stripe command, and then I can do another one. I can just say, all right, well, I'll just look at the output in the next stripe, and that's enough for that stripe. I'll just have one stripe there. And then what we'll do is let's look at some of the lower level signals. Let's go grab the internal signals to the inverter chain, and we'll put these together, and we'll throw in Y again one more time at the end. We'll have all those four together. And so this stripe command basically separates this group of signals here. They'll all be charted together. This one will be charted by itself, and these three signals will all be together in the same stripe. So to do that, what we'll do is we'll run the charts command, and we'll give it the original netlist name. That's all it needs, and we'll run that. And I accidentally typed in the wrong file, so we'll give it the right file name. So what it did was it created a chart. There's some controls in here that I can use to configure the chart. I can move the boundaries in and use a little more room at the top. It's got zoom control, so we can zoom in on one particular time point and see the different results. We'll zoom in a little bit more here. So now I can see the waveforms across process, and so this is something that can be extended for Monte Carlo analysis or mismatch analysis, but this is a great way to look at a lot of different kinds of results together. You can compare one simulation to another. It's very flexible that way. Lets you go back in time, so you can compare results from one revision of your design to another, and see the progression of your design in the results. And you can store the file separately. So anytime you have a result that you want to archive, you can archive that off into a folder, come back and compare one result to another. Next, we're going to take a look at parasitic simulation. And what we'll be looking at is how to mix schematics and layout together to set up parasitic extraction simulation. And the key to that is the universal pin. So we'll apply a universal pin to a test bench, and then we'll run the simulation and look at the waveforms. So we'll come back to our analysis here, and we'll save this file. Close this down for now, and we'll go back to our layout view. And so what we want to do is extract not only the devices that we intend, but the parasitics in between them. So there's a parasitic resistance of this polysilicon line between the output of this gate and the input of this gate. So those parasitics have to be calculated, and also there's capacitance between the polysilicon and the substrate. So all those things add up, and they slow down the device and slow down the simulation of slow down the functioning of the circuit. So what we do is we want to make a layout that has the proper stimulus. So one thing that's wrong with this test bench is that my ground connection isn't connected to the source. If I zoom in here, I can see that my VSS is left open, and I want to tie it to this ground so that it's held at the right voltage. So to do that, if I try connecting a schematic directly to a layout, it just says nothing added, no wiring done, because this is essentially a different technology. They're from two different worlds, so the schematic can't talk directly to the layout. So there needs to be a go-between, and the way we do that is with a miscellaneous element called a universal pin. So I'm going to drop down a universal pin right here, and if I can wire anything to a universal pin, so I can wire metal to it. So I've got a little tab of metal connected to that pin, and I can also connect my schematic to it. So now if I come in here and name this wire VSS, I've now got the proper connection between the stimulus world of electrical stimulus and my layout. And so that's pretty much it. I can run a simulation. Everything works as it does in the schematic. I can look at my waveforms and any of my signals and waves that were saved. Are managed between the layout and the schematic as well. So if I select that cell and I look at my result, there's my waveform with parasitics. And they are just a little bit soupier than the schematic version because they include all of the parasitic interactions and the interconnect. So things are just not quite as sharp as they are in the schematic world. And that's what we expect. So that took us all the way through to parasitic simulation. So finally what we'll do is we're going to look at some drafting tips and tricks. So in electric, it's most electronic design automation tools have their differences. Electric is more different from most other IC drafting tools that I've used, and that includes Synopsys, Mentor, Magma, Cadence, and it has a few concepts that are very different from the germane commercial tools that are used more often. So it's so what we have is a few tips and tricks that we'll cover really quickly, and we'll start with the layout because that's where a lot of the drafting expertise is needed. So we'll look at wiring, and again, it's basically left mouse button to right mouse button, start to end. We'll look at how to manage arcs in particular, and how to insert jogs in them so that you can work your way around obstacles. And then we'll also look at some of the attributes of an arc and how they affect the connectivity, especially when you're using very wide arcs. So for wide metal things, if you have a connection that might be 100 microns wide when you're connecting to a pad or you're connecting to a bus. So there's some things that are not intuitive that we'll show. And then we'll look at, we did review some of the body contacts, but we'll also look at well blankets, and they're more of an issue when it comes time to manufacture, but we'll show the relationships between well blankets and body contacts. There is a heuristic there that is hard to see. And then we'll look at how to build multi-finger transistors. There are widgets for that where we can generate multi-finger transistors very quickly. And then we'll look at the change command, which can be very handy for changing a lot of different things in the layout. We'll look quickly at polylines and icons. Those are some of the more difficult things to get used to at the very beginning. But once you get the hang of the artwork kit, it's very easy to use. But there's just a few things that aren't typical. And then we'll look at schematics and finish up with the auto connect feature, which is really important, especially when you're rewiring a device into a particular location on your schematic. For this next section, I've added a key monitor in the upper right hand corner. So what this will do is this will display the mouse buttons that I'm and my keyboard commands as I go along. So what we're going to do is we're going to go back to our Explorer and let's look at the layout view of this cell. And again, one of the key elements for working with drafting is you start with the left mouse button. So you can see I've clicked my left mouse button. If I want to continue this trace on this bus, for example, and I hit my right mouse button, that continues. So if I want to keep continuing, I just keep hitting my right mouse button. So that's an important thing. A really valuable aspect of electric is the undo. So I can undo something, and that's Control Z, and that's really important. If an environment doesn't support undo and redo, it's not finished, in my opinion. You need to have those features to be truly productive in a drafting environment. So that's an important feature. When creating arcs, very often, because of the way they're tied together, if I grab this metal, it has a fixed end-to-end connection. So, which is generally what you want. But what that leaves us with is a situation very often where we want things offset. So if I select any arc, I can insert a jog in it, and it creates this little slider box. And wherever I drop that box down, it's now created an arc segment. So now, if I move that up, what I want to do is move this end up. Now that jog arc is there, and I'm now routing around it. So that's an important trick to use for working with arcs. The other thing is, for example, if I drop down a component like a poly 1 to metal contact, and I make it let's say I make it very tall, so I make it a 20, and now when I route my metal from there, you can see that there's the way it's set up is that the start of it has no overlap, but the end does. So I can take this wire and I can toggle that. I can say, no, I want there to be overlap on the contact side. So I can toggle the head and have overlap at that end, or I can turn it off. I can overlap the tail, or I can turn them both on and both off. So depending on what you're doing, if you're routing from thick metal to thin metal, you may want to turn the tail over, the head and tail overlap on and off. And so these toggle buttons are very important for that and understanding how to do that. We had briefly covered how to connect to a transistor backgate by selecting a transistor using the special select. I can now get to the backgate and tie to the back as well. But what you can see has happened, and again, this is more of a manufacturing issue than it is a design issue. But in the creation of this layout, I have these ragged geometries. And for design for manufacturability, although all the rules are satisfied, DRC is satisfied. It's a perfectly valid design. In general, these ragged edges create more problems than they solve. So what we can do is we can put down what's called a pure layer. And a pure layer, so let's put down those are p-channel devices. So what we're going to do is we're going to put down a pure NWell layer node here, and I'm going to set it to something very long. So my X, let's make it 100 by 30. And if I put that down, now I have a blanket NWell over my P devices, and in that way I get a very homogeneous geometry. When this is exported out to GDS2, all the elements are merged together into one geometry. So this saves a lot of disk space in GDS2. It makes the manufacturing and the pattern generation much easier, and so it's a common practice to do it that way. Again, if I'm in normal select mode, if I'm in my normal select mode, I can't move these well shapes. In order to move them, I need to use the special select to move them around. So, and that's basically so that I can move transistors on top of these blankets without interfering with the selection mode. But if I do need to move the well itself, just remember to go to the special select. Once I'm out of special select, they're essentially fixed. Everything I need to make an N transistor I can find along this row in the menu. So if I go here and I grab an NMOS device, I can hit Control-I and I can change the width or the length. So we'll make this a 20 by 4 transistor. And I'll need, since it's an NMOS, I'm going to need an N-active contact for it. And I'll make this a 20 in width so it matches. So connecting, I'll need one for the drain as well. So connecting these are very easy. So if I look at the connection here, I select it. The pin is highlighted here, so I'm using right mouse button to select that connection. Left mouse button, then finish with right. Those two are connected. Now that arc in the middle looks very narrow, but if I reduce the length to 0, it will satisfy the rules. And likewise, if I connect here to here, I can walk it in, and I've got an N transistor. So there's the simplest construction of a transistor. Now, if I want to make a multi-finger transistor, that can become fairly tedious. So let's say I'm doing a Phil Allen lab and I'm making a current mirror. Well, I would want to have many of these devices together. Well, there's a tool for that. So if I go under Tools and I go under Generation, I can look for a multi-finger transistor. And again, the tool is going to encourage the use of hierarchy, so it's going to create a cell for it. And so I'm going to make an N transistor device. It's going to pull that contact. I'm going to make a length, let's do, based on the cell we have here, a 4 by 20. And the number of fingers, let's make it a 20-finger transistor. And I can add a little bit of extra poly on the end. So let's add 1 micron or one lambda of poly. And what it's done is it's generated that transistor design for me in a multi-finger cell. So so a lot of the tedious work, if I want to come in here and tie all these together as one gate, I can do that. And so the general idea is that by using the finger cell and hierarchy, you can accomplish a lot of the scalability aspects of analog design. Another important tool is the change command. So if I select a device and I hit Control-C, hit the C, I can basically say change only selected devices, and I can say, okay, I'm going to make this into, let's just make it a P transistor. And I change it, it's been morphed over to a P transistor. So that probably won't satisfy DRC or LVS, but the idea is you can change just the ones that you selected. You can change everything in a library. You can change anything in a cell. Change everything in all libraries. So use with caution, but it does come in very handy to be able to change one object type for another, and especially for complementary designs where you might have designed a current mirror in as an N channel, switching it over to a P channel is fairly straightforward to do. So lastly, we're going to look at some tricks in the schematic we've seen some of those thus far, but again, it's important to know some of the more important tricks. We've looked at connection tracing and editing instances and wiring in schematics, but there's one more trick which is called the auto connect feature, which is very handy. So if I take a device and let's say I delete this device out of it, and I can come back and say, oh well, I'm gonna put a transistor back in there. Well, how do I do that? So if I come grab my transistor and drop it in place, we'll zoom in to get a better look at it. I've picked the wrong transistor, so I'm going to go pick my N-channel transistor. So it would appear that this device is in place, but it's not. And one of the giveaways that it's not connected is that I can see the port names. I can see the letter G for gate, S for source, D for drain, and B for backgate. So if you see a character like that, a large character, it's meant to do that so it's obvious that it's not properly connected. So once it's in place, this is a special case where I've got putting the same device back. But simply by hitting F2, what it's going to do is it's going to connect by proximity. It's going to say, okay, I'm going to reconnect that in, and so now if I go in here and I hit Control I, I can select my parameters and I can look that I have this device. I want it to have 4 fingers, a width of 3, and now I've got my transistor back the way I want it. So that's the F2 is this auto connect feature that automatically connects things together. F2 also works in layout. Use it cautiously because it'll connect things you might not expect. But remember, DRC and LVS is there to help you through the connectivity verification. So all those things are in place to make sure that any mistakes you do make, you're gonna catch them eventually. But auto connect is handy, but it's also, you got to be careful. Make sure that you take a look at what's just transpired between the command and the database. Finally, we'll look at how to modify a symbol. So the way this kit is delivered, you can edit the kit, and good, bad, or indifferent, that's the way it's delivered. And so if I go into this N transistor, I may not like the color black. I may want blue or purple. So if I go to my P transistor, for example, I've got an icon here. If I don't like to have this inversion symbol here, then I can delete it and it's gone, or I can undo and bring it back. One of the things that's important to keep in mind is that some of the components in the artwork library are special. So for example, this multi-line here, if I bring this in, the only way to really edit this is to select this pencil button, which lets you toggle the outline. And you can see that once you're in that mode, you can edit this. You can put in other points and bring that in that way. So there's a lot of different things that you can do to modify the picture and embellish. You can work with the text. You can underline text. You can use different fonts. This particular symbol is using all the defaults. So that's just how it was set up. But exports are special in that they define what the I/O of a particular cell is, and Electric expects the I/O of the icon, the schematic, and the layout to all be identical. That's a key element in making LVS work. So you'll get lots of errors and warnings if they don't match. So in conclusion, we've covered the tips and tricks for doing drafting, and that concludes this training video. If you have any questions, please forward them to holmes@sherlockmbv.com, and we'll take inputs on what should go into version 0.2, and look forward to hearing from you. Thank you for your time.